Hello again, guys. We are here on 5.8 with simplifying radicals. And this property is, it appears in the Pearson module, and hopefully you are working through that and getting up to the got it in problem 1. So what we want to look at here is how we use our algebraic methods to simplify radicals, especially non-perfect squares. So what we see is any radical that I can find the product of. So as long as it's the radical of a non-prime number, a composite, we can figure out the product of those two numbers. So let's say 48. The product is 16 and 3 that makes 48, or the two terms of the product. And then we can find a perfect square of the 16, take that, find its 4, and then the non-perfect square 3 just stays under the radical. So try that method here on the got it for problem 1. What perfect square and what other number would multiply together to give us 72? Pause the video and give that a shot. So what we see here then is when we think about breaking down 72, we can set it up as 36 times 2, which then I can split those into two separate radicals, and then the square root of 36 is 6, and we have 6 radical, I have a typo, 6 radical 32, 6 radical 2, if I can ever say this correctly. So try the same with radical 225 and negative 4 radical 117. We want to simplify both of these. Alright, this method also helps us with larger radicals that may or may not be perfect squares. So 225 is in fact a perfect square, but let's say you did not know that. We can think of it as being 25 times 9, which would give us 225, and what our indicator that points us in the direction of this being a perfect square is that radical 225 is 5. Radical 9 is 3. So I can actually take the square root of both of those, and 5 times 3 is 15, which tells me that up here, actually radical 225 is 15, so it is a perfect square. Simplify number 2. Pause the video and do that if you have not yet. So if you think through the factors that could multiply to give us 117, our first one of the perfect square is actually 9 times 13. So then when we break these up, we'll have negative 4 on the outside times radical 9 times radical 13. And radical 9 can be reduced to a 3. So we now have negative 4 times 3 times radical 13. And that, we go ahead and combine the negative 4 and the positive 3, and we get negative 12. Making all kinds of typos. So we get negative 12 times radical 13. So go ahead, work through the Pearson module for part 2, and then come back on the got it. Alright, hopefully something else you've gathered from the Pearson module is that a square root, a radical, is essentially like a power of 1/2. So what that does to variable factors that have powers is we want to get that variable to an even number, so then I can take half of it. So we could rewrite this as negative m, and let's go ahead and look at the 80 as well and say, can we break that up into two factors that would multiply into 80, one of which being a perfect square? Those factors would in fact be 16 times 5, 16 being the perfect square, of course. Then I can just rewrite my m to the 9th as m to the 8th times m, just taking one of the m's away from the power. So now we can apply this half power and rewrite everything. So now this becomes negative m times the radical of 16 is 4. My 5 is a non-perfect square, so it stays under the radical. M to the 8th, well, that to the 1/2 power is really going to be m to the 4th. And then the other m is going to stay under the radical. So now let's tidy this up and make it look a little better. My like terms can all come together, or at least in front of the variables. So I have a variable term and a variable term. I can combine these. This negative, again, is really like a negative 1. So that can go on the 4. So we can say it's negative 4 m to the 5th radical 5m. Go ahead, pause the video, try 3 and 4, and then come back for the answers. Alright, on number 3, I'm going to show this in a little bit nicer of an order. Let's take everything out of the radical that we can first. So I can take the 25 out and just call that 5. And then I can take t to the 4th out, and again we chop the power in half, and it's just t squared. Now let's leave everything that stays under the radical, so the 2 stayed under, and the other t stayed under. So if you have yet to do it, pause and do number 4. Alright, so if we're looking at number 4, I've broken everything up now. The first perfect square that is a product of 243 is actually 81. So 81 times 3 would give us our 243. My y squared times my y, that would give me the y cubed. So now I start to break things and bring them out of the radical. So radical 81, that's 9. I'm going to skip the 3 for a moment. Radical y squared is just y. Then I come back, get that 3 and the other y under the radical, and then I'm going to clean this up. Negative 2 times 9 will give me negative 18 y radical 3y. That's how we do that. Work through the Pearson module for problem 3 until you get to the got it, and then come back if you need help. Alright, so on the problem 3 got it here, we are looking at multiplying two radical expressions. So in order to do that, we would like to first multiply anything outside the radicals together and then multiply everything inside the radicals together. So remember that there's really a 1 out in front of any radical, just like a coefficient to a variable. So the outside of my radicals will still be 3, but the inside will now be 6 times 18. I multiply my 6 by my 18 and I get 108. I then think about the factors of 108 and realize that 36 and 3 will get me multiplied to 108. I can then take the radical of my 36 and say that that is 6. Radical 3 stays under the radical, and 3 times 6 gives me 18 times radical 3. And that is my simplified form of the sum of the radicals. Try that on B and C if you have not done that yet. What you'll see on B is kind of funny. We go ahead, we multiply the inside of the radicals together. We get 18a to the 4th, and we break it back up to the 9 and the 2 because that's the first perfect square in the product of 18. But the a to the 4th now, this has helped me because I can bring the a to the 4th out and rewrite this as 3 times a squared times radical 2. If you haven't done so yet, do number C. Alright, you got to start paying very careful attention to details here because there's a lot of steps. We take the 7 times the 3, that's going to give me a 21 out in front of my radical. Then inside the radical I have the 5 and the 20 from the original, so 5 times 20 is 100. And then the x times x to the 5th gives me x to the 6th. That all then, the radical 100 can simplify to a 10. Radical of x to the 6th. Remember, we cut it in half, so instead of x to the 6, it's x to the 6 divided by 2, which we can rewrite as just x to the 3rd down here. So 21 times 10 is 210 times x to the 3rd. Try 5 and 6 down here for extra practice, and come back for just the answer. So here's the answer for number 5. Looking at number 6 here, it's a little bit more difficult. So pause and try it on your own, but I'm going to start highlighting some things to make life easier. Alright, if I look at the highlighted version of what I have now, it kind of helps us keep things straight. Negative 1/3, negative 6, because they're out in front of the radical, go together. The 18 and the 8 go together inside here, and the c to the 5th and c to the 9th also go together. So now we have 2 on the outside of the radical. Inside the radical, 18 times 8 picks up to be 144. C to the 5th times c to the 9th, where we add those exponents, so we get c to the 14th. And I'll take the radical of 144, and that is 12. And the radical of c to the 14th, we chop that exponent in half, and it's c to the 7th. So I get 24 times c to the 7th. Please work through the Pearson module for number 4, and then come back and visit for the got it problem. Alright, in this problem we're asked to look at the maximum length painting that would fit through a door with a height 4 times its width. So if we know that the height is 4 times the width, we could label these things like W and 4W. And we know that the largest span of a doorway is the diagonal. Now, if you remember the Pythagorean theorem, Pythagorean theorem tells me that the hypotenuse of any triangle is the sum of the squares of its sides. So go ahead, set up what the length of that hypotenuse would be. And of course what I meant to say was that the square of the hypotenuse is equal to the sum of the squares of the legs. So if I take my two legs and I look at squaring them, I'm going to get 16w squared, and then w squared is just another w squared. But since this is the square of the hypotenuse, we will need to square root on both sides. That then will give me that c is equal to radical. Well, we might as well combine what's going to be in that radical. So 16w squared plus one more w squared equals 17w squared. Be careful, this is addition. Nothing happens with my w squared because they are the same base. It's like combining like terms now. So what we get is that c is equal, and I'm just going to rewrite the same thing over here for a moment. C is equal to radical w squared. And when I take the square root of what I can, I just get w times the radical of 17. Try this example problem here, number 7. Go ahead, pause the video while you can see this, and give it a shot real fast to make sure that you understand what we're doing. Alright, again, excuse my poor drawing because I'm still getting used to the Smart tab. But what we have here, knowing that the height of the frame is 6 times the width, is we have a 6w and a w, and we want to talk about the hypotenuse. Since we're talking about a length of a brace for right there, let's go ahead and talk about that as being L. So we know that the length of that brace squared would be my height and length, both squared, and then the sum of that. So go ahead and try that on your own. If you have not paused and solved this yet, do it now. Alright, same process as we did before. We should end up with the length of that brace being the width of the door, or the bottom of the door, times the radical 37. So we're going to use our division property of square roots next, and what that tells me is if there's a quotient inside a radical, that actually means that it's the radical or the square root of the numerator divided by the square root of the denominator. So when it's on the inside completely, we can split it and look at them separately, which makes my life easier in most situations. Please make sure you've worked through the Pearson module for problem 5, and then try the got it on your own before clicking play and coming back to us. So pause the video now. So what we see here is that the answer for A is 4, and B gets a little bit more complicated. So if you haven't tried this on your own yet, do so now. But when we're looking at solving it, we have the radical on top is not that hard. Radical 36 would just be 6, and then radical A cannot be simplified, so it's just radical A. Then on bottom, I can say radical of 4 is 2. A cubed I can think of as being A squared times A. So this A is going to stay under the radical, but this A squared can come out of the radical and become A. Now that I have radical A over radical A, these can cancel each other. So because these are both the same on top and bottom, they cancel out. And what I see when I simplify this fraction for 6 divided by 2 is I get 3 in the numerator and just A in the denominator. So there we go. Please make sure that you work through the Pearson Module 6 or Problem 6 before you try to dive right into the got it, because it won't make sense. So what we're trying to do is rationalize these denominators, which means this square root, square root of 3 especially, if it's a non-perfect square root, it is a non-rational number. However, I can rationalize it by taking it times itself. Now remember, we don't actually want to change anything, so I really multiply by 1, radical 3 over radical 3, but why I'm doing this is I'm multiplying by the denominator, which will then make the denominator a rational 3. My numerator has radical 2 times radical 3, which is going to give me radical 6, and that is it. So go ahead, try that with B and C. Pause the video and try on your own. The tricky part about B is that we now can actually simplify the denominator first. So we can see that radical 18m can be reduced because I can split it into radical 9 times 2m, take out the radical 9, which becomes 3, and I now have 3 times radical 2m, so go ahead, continue the process. Alright guys, I realized I have 20 seconds left, so I am just about out of time here. We split the radical to top and bottom, multiply by radical 3, and find our answer here. Down here we just multiply by radical 11 top and bottom, which makes my top radical 11 times 1, or just radical 11, then this over 11. And over here we see that we end up with a radical 7s canceling out on both top and bottom. Please make sure that you do your homework and let me know if you have any questions, comments, or concerns. Have a great day.